Welcome. This is Dr. G, and the purpose of this video is to both clarify and simplify logarithms. And instead of bombarding you with 10 to 15 log rules, I'm going to condense it to just 4 log rules that you have to know very well, and I'm going to show you when and where to use those log rules and how they make the other log rules kind of redundant. Enough said, let's go! When learning logarithms, it's important to keep in mind that they are closely related to exponents. In fact, they're inverses of each other. On top of that, logarithms can be just a common log or a natural log, ln. Let's first take a look at the relationship between common logs and exponents. Here, we see an inverse relationship between an exponential function and a logarithmic function. Notice how the exponential function has a base of 10, which is the same for our logarithmic function as well. What about natural logs? Here we can see the inverse relationship between an exponential function and a natural log function. Notice the bases of these two functions are again the same, except this time it's not a number, rather it's the letter e. E is known as Euler's number or Euler's constant, and it's just one big irrational number, kind of like pi. And natural logs will always have Euler's constant e as their base. Here you can see the basic layout of logarithmic equation, in which a here is the base, b is the argument, and c is the exponent. That's weird, right? We wouldn't normally associate the exponent with whatever c is. You'll see in just a few minutes why we can call it the exponent. On a side note, now that I think about it, it would have made much more sense if I had used the letter b for base and a for the argument. Unfortunately, all the animations are already done and it would take too long for me to change them. My bad. If a log has no base, it just means that the base is 10, the default basis for common logs. For ln or natural logs, there will never be a base written because there can only be one base, which is e, Euler's number. Another thing to note, all the rules for common logs also apply to natural logs, except the ones that of course changes the base because natural logs can only have e as their base. One last thing before we dive into the rules, and in my opinion, this is a fundamental idea all students should have when studying logarithms. Earlier, I mentioned that logarithms and exponents are inverses of each other. But that probably doesn't mean too much when you're doing mathematical questions involving logs and exponents. Actually, being inverses of each other plays a big role when it comes to solving questions involving exponents and logs. For example, when solving exponential equations, which is when we have the variable x in the exponent position, we would have to use logarithms to have a chance at solving for x. And if we do use logarithms, we'll end up with something that looks like this. And while I'm not going to go any further right now, we will come back to this in just a bit. Conversely, when we're solving logarithmic equations, which is when we have common logs or natural logs in the equation, we will want to use exponents in order to solve for x. And when we do, it will look something like this. Again, I'm not going to solve for it now, but you can see it's not that hard to solve for x at this point. Now let's officially start log rules. As you can see on the screen, there is an overwhelming number of log rules, a lot of which don't even have names, so I grouped them under miscellaneous rules. But in my opinion, there's really only just 4 rules that you have to know because all the other rules are either related to it or redundant if you know these 4 rules well. You might be thinking that I'm cheating because I'm putting product rule and quotient rule as one single rule here, but there's a reason for that because I actually think it's better to think of them as one rule than 2 separate rules. The first rule we're going to talk about is the definition of logarithms, and this is by far the most important one. We already established that logarithms and exponents are related because they're inverses, but that inverse relationship manifests in the fact that we can have 2 different forms when dealing with logarithmic and exponential equations. The logarithmic form we've already seen, where the base is a, the argument is b, and the exponent is c. We're able to shuffle this into the exponential form, where the base stays as a. The exponent c is now actually in the exponent slot, which makes sense now. And our argument b is on its own. And like all log rules, it can be converted back and forth. Now let's see where we can use this. First, what if I have log base 2 of 128 and want to know what it is? One way I can do this is to make it equal to x and make my own equation. And that's fair because whatever log base 2 of 128 is now represented by x, so all I have to do is solve for x. Once I have this, I can see that I have my logarithmic form, and I can rearrange it and shuffle it to make it look like the exponential form, in which case the x is the exponent, so now I'm asking myself 2 to the power of what is 128, and that would be 7. And since I said that log base 2 of 128 is x, and my x is 7, that would have to mean that log base 2 of 128 is just 7. Another example is, what if I have a number 3, but I really want to write it as a log with a base of, let's say, 5? What would my argument have to be? Since I don't know, I could set it as x. And now I have a logarithmic equation. Well, first of all, I'm going to move it to the left, just a personal preference. And I can rearrange it so that I can turn it into the exponential form. And I can solve for x, which is 125, which means the argument x would have to be 125. So 3 can be written as log base 5 of 125. On a side note, what if you have log x equals 3 and you want to solve for x? Notice there's no base here, but we did learn that if there is no base, it has to be the default base of 10. So now we can shuffle this into the exponential form and easily solve for x, which is 1000, which means log of 1000 is 3. Now let's revisit this slide when we're solving logarithmic equations, and I said that we can use exponents to make it look something like x plus 1 equals 10 to the power of 3. How did we get there? Well, the answer is we used the first log rule. As you can see, there's no base, which means the base would have to be 10. And now that I have a logarithmic form, I can easily convert it to the exponential form, and a quick rearrangement leaves me with x plus 1 equals 10 to the power of 3, which is what we had earlier. The definition of the log rule is not only important because we use it so much, but it's also important because it renders a lot of other log rules redundant. For example, there is a log of 1 rule that states the log of a base of 1 is always equal to 0. Now don't get me wrong, these redundant rules I'm about to mention are all great and you can easily memorize them once you have a good understanding of logs. It's just that when they're all thrown at you in the beginning, you wouldn't know what's more important than the other, so it's overwhelming. As you can see here, I can easily rearrange this into the exponential form, and now it reads that the base a to the power of 0 is 1, which is of course true because that's literally the 0 exponent rule. Anything to the power of 0 is 1. So when you see log base 2 of 1, and if you remember that it's 0 based on the rule, that's great. But what if you forget? That's okay. You can set it to equal to x, and now you can rearrange it into the exponential form and ask yourself 2 to the power of what is 1? What has to be 0? So now you know that log base 2 of 1 is 0. Another redundant rule is the log of the same base rule that states that if your base and argument is the same, then it's always equal to 1. Again, great rule to remember once you have everything down, but it's easily replaceable by our definition of the logarithms because once we rearrange it in the exponential form, it becomes obvious that a base to the power of 1 is going to be itself. So if you see log base 2 of 2 and notice that the base and the argument matches, then you know it's 1. And if you see log 10, remember the base is 10 here, it's also equal to 1. And the natural log or ln of e, again with the base of e, is 1. Another rule that I'm not a big fan of because it's quite redundant. This is the number raised to the log rule, and it states that if you have a logarithm in the exponent and the base of the logarithm matches the base of our exponent, then we can cross out the entire thing, leaving us with only the argument. Let's take a look at an example. Suppose we have log base 5 of x is equal to 3. Let's try to solve for x. Using what we just learned, we can raise both sides as exponent with a base of 5 strategically because we want to match our exponent base of 5 with a logarithmic base of 5. That allows us to cross out the entire thing here, leaving us with x is equal to 5 to the power of 3. But can we not do this using the definition of the logs? Can we not rearrange this logarithmic equation into the exponential form and solve for x that way, which gives us the exact same answer? Okay, let's take it a step further. What if we have logs on both sides of the equal sign? Again, there's multiple ways of solving this. The first way again is to raise both sides an exponent with a base of 5. That way we can cross out both logs, leaving us with only the arguments of 2x equals to x plus 4. But believe it or not, there's another rule that helps us tackle this question called the equality rule, and it's super redundant as well. It states that log base a of b is equal to log base a of c, which means that if your bases match, then the arguments would have to equal to each other. Well, no duh, if you ask yourself log base 2 of 5 is equal to log base 2 of what, it would have to be 5, wouldn't it? So this means whenever you have a log on both sides with the same bases, we can just cross out the logs and make the arguments equal to each other. Back to the example, now we know to cross out the logs on both sides without having to raise both sides as exponent with a base of 5 like we did on the left side, and that leaves us with the exact same thing of 2x is equal to x plus 4. Keep in mind though, both of these rules only work if our bases are the same. If you see something like this here with one base as a 6 and the other base as 5, you can't raise one side with a base of 6 and the other side with a base of 5 and cross them out because we're not doing the same thing to both sides. Conversely, you cannot just simply cross out the logs on both sides just because you see a log, because their bases are unfortunately different. That wraps up the first main rule we have to learn, which is the definition of the log. And now let's move on to the second rule, which is the power rule. The power rule, quite honestly, is pretty cool and very hard to forget, and as you expect, we use it very often when dealing with logs. The power rule states that if you have an argument with its own exponent, that exponent can be moved in front of the log as a coefficient. So that means if we have log of x squared, that squared can be moved to the front as a 2. But be careful, if your entire log x is being squared, that squared isn't for your argument, it's for your entire log. So we can't move that 2 to the front. Instead, it's basically log x times log x. Right off the bat, the power rule renders the log of a reciprocal rule absolutely useless. The log of the reciprocal rule states that a negative log base a of b is equal to log base a of 1 over b, which admittedly at first glance might seem really cool and important, but it's actually not, because if you have negative log base a of b, that negative is actually a negative 1. So can we not reverse a power rule and move it up as an exponent for our argument being negative 1? And what is b to the power of negative 1? Well, using our exponent rule, we know that that's the same as 1 over b. The cool part of the power rule is that it allows us to pretty much rescue any variables we have in the exponent slot. This is pretty tough to solve for using algebra because our x variable is in the exponent slot. Wouldn't it be great if we can move this x down to the coefficient slot? Well, since I can't just bring down the x like this, I can maybe introduce logs to both sides, remind you, otherwise it wouldn't be fair. And once I have log 3 to the power of x, that x now can be brought down as a coefficient. In other words, we rescue the x from the exponent slot down to the coefficient slot. And now we can easily solve for x by dividing both sides by log 3, and we'll have our answer for x. And this is actually the reason why we use logarithms when we're trying to solve for exponential equations. Remember this screen? When we had x's in the exponent slots and I said to use logarithms? It's all because of a rescue mission using the power rule to bring down the x's to the coefficient slots. Let's see what we can do here. First thing is I have to introduce logs, otherwise I can't do anything with my x's, so I would have to log both sides. And by doing that, I can now rescue my exponents down to the coefficient slots using the power rule. And at this point, it becomes just algebra. I can distribute the left-hand side to break the bracket and group up the terms with x's on the left-hand side. This way I can factor out the greatest common factor, which is my x, and finally isolate my x, getting whatever the heck this is. And that wraps up the super simple but super important power rule. Next up is the product rule and quotient rule. Like I said before, I prefer to think of those two as one rule, but for the sake of technicality, let's take a look at them individually, starting with the product rule. The product rule states that if you have a log base a of an argument that's xy, then we can expand it into two logs, one being log base a of x plus log base a of y. And like all log rules, but especially important for product and quotient rules, we can go both ways. Some common mistakes when using the product rule is when you have log of x and y, for example, students accidentally expand it into log x times log y when it should have been log x plus log y. Or when we see log x plus log y, they condense it into log of x plus y instead of log xy. Both of these, of course, are incorrect. Now let's take a look at the quotient rule. The quotient rule states that if you have a log base a of an argument that's x over y, then it expands into log base a of x minus log base a of y. Again, just like the product rule, the quotient rule can also be applied both ways. Some common mistakes in the quotient rule includes when you're expanding the log of x over y, you make it log x over log y instead of log x minus log y. And if you have log x minus log y, you accidentally condense it into log of x minus y instead of log x over log y, both of which again is incorrect. So now here's the thing. I really dislike the product rule and the quotient rule when they're taught this way because it feels very mechanical. In my opinion, it's best to look at these two rules as one rule and just think to yourself, it's either I have one log and I want to expand it into multiple logs. The plus signs and the minus signs will be dictated by whether or not I'm using the product or quotient rule. And if I have multiple logs, I can condense it into a single log. Let's take a look at an example of expansion. Here I see a single log, which means I would have to expand. Looking at my argument, I see a huge fraction with numbers and letters on both the numerator and the denominator, which makes it very challenging if your mind's fixated on using either the product or the quotient rule. The better way would be to focus on the numerator and the denominator of that fraction separately. All the numbers and letters on the numerator will get their own positive logs, and everything on the denominator will get their own negative logs. Now we can just arrange the logs all together. The order doesn't matter at all. And to finish it up, we can cross out the redundant plus sign in the beginning, and we can move the exponent to the front here using the power rule because we generally don't like to have exponents on our arguments. So our final answer would look something like this. On the other hand, what if you see a question like this? Well, since there's 3 logs here, the only thing we can do is to condense into a single log, right? But before we can do that, we have to first look at these 2 problems. When we're condensing, we don't like to have coefficients like 2, nor do we like to have any roots. So we can easily fix that by moving the 2 to the exponent of our argument using the power rule, and we can rewrite the root as x to the power of 3 over 2. Now, we can just write a single log with a base of 5, of course, and put a huge horizontal fraction line. Whichever arguments have positive logs would go on the top, and the arguments with negative logs will go on the bottom. So we can rearrange them just like this. And of course, we can clean it up a little bit using exponent laws. This question might look different, but it's the same thing. We see 2 logs here, so we have to condense it into a single log. The term on the left, x squared minus 16, has a positive log, while the x squared minus 2x minus 8 has a negative log. So when we condense it, it would look something like this. Now we can factor both the numerator and the denominator, giving us something that looks like this. And of course, we can cross out the brackets that are identical, which are the x minus 4s, leaving us with the final answer of this. This is a question that you typically run into when doing log rules. Suppose log 3 is p and log 7 is q. They'll ask you to express log 30 root 7 in terms of only p and q. Alright, let's start by looking at log 30 root 7. The 30 looks like it has a chance to become a p somehow, and the root 7 looks like it's destined to become a q of some sort. Since we have a single log here, we would have to expand it into 2 different logs, and since both of these arguments are technically in the numerator because we don't have a denominator, they both get positive logs like this. At this point, we can fix up both of these logs. The 30 can be written as log 3 times 10, and the log root 7 can be written differently because we don't like roots when we're doing logs. So now we can expand the log 30 into log 10 plus log 3 and can rewrite the log root 7 as log 7 to the power of a half. We're almost there. At this point, we should look at log 10 and think, hold on a second, isn't the base and my argument the same? Which means log 10 is just 1. In terms of log 3, well, that's just p. And for log 7 to the power of a half, we can apply the power rule. So putting that all together, our expression looks like 1 plus p plus half log 7. And since log 7 is literally q, our final answer should be 1 plus p plus half q. This wraps up the product rule and the quotient rule, leaving us with only one important rule left, that is the change of base rule. Unlike the other 3 log rules that we have to pretty much use one way or another whenever we do log questions, the base change rule is more specific for certain situations, but it does open up the door to tackle more difficult logarithmic questions. What is the rule? Well, the base change rule states that if you have a log with base a of b, you can write it as 2 separate logs, but most importantly is we can now introduce a brand new base. One way to remember this is our original argument is situated above the base, so that when they split into their own logs, the log with our original argument is going to be on the numerator, which is above the log with our original base, which is the denominator. Notice now we have a chance to introduce a brand new base of our choice, whatever number you want. Suppose we have log base 2 of 5. How will we figure out what this is? Well, if you remember from the very first log rule, we can set it to equal to x, creating a logarithmic equation, and rearrange it in the exponential form. But the problem is x is very difficult to figure out here because 2 and 5 aren't exactly in the same family of numbers. On the other hand, we can try to use a calculator, but unfortunately, most scientific calculators can only deal with logs and lns in their default bases, which means the logs in calculators can only have a base of 10, and lns, of course, will always have a base of e. So let's try our change of base rule here. Instead of writing it as log base 2 of 5, we can write it as 2 separate logs with log base 10 of 5 over log base 10 of 2. I now introduced a friendlier base that's 10, so I can use it in my calculator. Now, of course, I don't have to write the 10 out, so it can look like this, log 5 over log 2. And at that point, I can just go ahead and punch it into my calculator to get the answer. Another situation where we need to use a change of base rule is for questions like this. Suppose they say that log base 3 of 5 is A and log base 3 of 2 is B, but we want to express log 80 in terms of A and B. Right off the bat, we have a problem. Log 80 has a base of 10, but the logs in the question all have bases of 3. There are completely different waveforms here. So it's up to us to change the log 80 into a log with a base of 3. And to do that, we can do log base 3 of 80 over log base 3 of 10. And at that point, we can split apart 80 and 10 into 5 times 16 and 5 times 2. And we can expand both the top and the bottom logs like this. At that point, we unlock log base 3 of 5 on the top and the bottom, as well as log base 3 of 2 on the bottom, so we can replace them with A and B's respectively. Notice I rewrote log base 3 of 16 as log base 3 of 2 to the power of 4, so I can apply the power rule and bring the 4 to the front, unlocking yet again a log base 3 of 2, which is B, so our final answer would look like this. Here's a log rule that is completely redundant because of the change of base rule that we know. I don't even know the name of this rule. It states that log base A of B times log base B of C is log base A of C. Let's do this using the change of base rule. You see log base A of B can be written as log B over log A, and I'm just going to use the base of 10 here, times log C over log B, and we can cancel out the log B's, leaving us with log C over log A, which we can write combined as log base A of C. Here's a rule that's actually worth remembering, but it's explained again easily by our change of base. It states that log with a base of A to its own exponent E of X can be written as 1 over E log base A of X. Here's how the change of base rule can easily explain this to us. We can first rewrite this as 2 separate logs, and now we can use the power rule to bring the E as a coefficient, and with a coefficient of 1 over E, we can rewrite it as log base A of X. And it doesn't stop here. We can move the 1 over E back up as an exponent using the power rule, so then we can have log base A of X to the power of 1 over E. So technically, when we started with log base A to the power of EX, we can turn it into log base A X to the power of 1 over E. Again, all of this might look really intimidating and random, but it's not. It's all just a change of base rule at work. Notice all the bases here are different, but they're all in the same family, which is the family of 2. So we can rewrite these bases all as 2 to the power of something. 16 becomes 2 to the power of 4, 8 becomes 2 to the power of 3, and 1 over 4 becomes 2 to the power of negative 2. Using that rule we just learned, we can rewrite these like this. Notice the 4 becomes 1 over 4 as a coefficient, the 3 becomes 1 over 3, and the negative 2 becomes minus 1 over 2. At this point, we can now move these coefficients back up as a power rule, and now since all the logs have no coefficients with same bases, we can condense them into a single log using the reverse quotient and product rule. The arguments with the positive logs will go on the numerator, and the argument c to the power 1/2 that has a negative log goes on the denominator, and that'll be your final simplified answer. This rule, I think, is super redundant. It's pretty much the same as the earlier rule we just saw, but this time our argument also has an exponent, so it's just an extra power rule. It states that log base a to its power of e of x to the power of I can be written as I over e log base a of x. And you can probably already see that coming. How do we show this? We can again use the change of base rule and split this into 2 separate logs. And now we can do power rule to the top and the bottom to move the I and the e to its coefficient spots. And now, of course, our coefficient is 1 over e, and we have again log base a of x. The base switch rule is quite interesting because it's not very hard to memorize. It's very unique, but it's actually related to the base change rule. It states that the log base a of b can be written as 1 over the log base b of a. Notice the argument in the base switch spots, but we have to put it underneath 1. Again, we could also use the base change rule here to show this. Log base a of b can be written as log b over log a with a common base of c, let's say. And now I can put the entire fraction under 1. When I want to do that, I would have to flip the log b and the log a so it's reversed. And now I can rewrite the denominator as a single log base b of a using the base change rule. Here's an application of the base switch rule. Notice that the base and the arguments are completely flipped in the 2 logs. That is a red flag. So we can apply the base switch rule here. We'll leave the first log the same. In the second log, we will switch the base and the argument at the cost, of course, of putting it as a fraction underneath 1. At this point, it's just algebra. We're going to multiply everything by the lowest common denominator, which happens to be log base 3 of x, which crosses out the log base 3 of x in the denominator. Be careful on the left here. When you see log base 3 of x multiplying by log base 3 of x, you might accidentally write it as log base 3 of x squared with the squared attached to the x. That's not true. Because we're multiplying two logs, we would have to put it in brackets with the squared on the outside. We can now rearrange this equation to make it look like this, and this is actually a factorable trinomial, but we're not going to get into that in this video. And this wraps up the change of base rule and pretty much all the log rules you need to know. If you like this video, consider subscribing to my YouTube channel and also follow me on my other social media platforms.